So from the last section, we did ask you to bring back a couple of problems to me with answers. So I'll go ahead and give you the answers. For on page 4, if you had $8,000 invested at 7% for 15 years, compounded quarterly, that means N would have been 4. So you would have gotten A is approximately $22,654.53. And then if you're compounded monthly, N would have been 12. So A would have been approximately, if we're rounding to near cent, $22,791.57. And if you're compounded continuously, you need to use the formula A equaling PE raised to the RT. And so your A is going to be approximately $22,861.21. So there are the answers to the 3 that I asked for you to bring back to me last time. And then I think all that was done on page 5. So let's go ahead and move on to 4.2. So 4.2 is over logarithmic functions and their graphs. Now, first of all, we need to know, what do you mean by a logarithmic? That's a new word that we might not have heard before. So before we get into that, let's just go back to exponential functions. And we want to know, do they have inverses? So if you remember back to the previous section, 4.1, all exponential graphs had this type of shape. I want to know, do those functions have inverses? Well, from previous sections, to know if something has an inverse, it has to be a one-to-one function. So it definitely is a function because it passes a vertical line test. It is a one-to-one function because it passes the horizontal line test. So yes, exponential functions have inverses because it passes the horizontal line test. Well, again, back in a previous chapter, we learned how we could find the inverse function. Well, instead of f of x, we call it y. And then we interchange x and y, so this becomes a y and this becomes an x, and we get x equaling 2 to the y, and somehow we're supposed to solve for y. But we've never really solved for a variable up in the exponent. Some people want to take the yth root, but then that makes the yth the index. So there's really no way to solve for y at this point. We don't have that in our book of knowledge. But we can still graph it, because if we know the graph of the exponential, then we just flip-flop the x and the y, we'll get the graph of the inverse. So this is your symbol for inverse. So let's go ahead and plug in a 0. So 2 to the 0 power is 1, 2 to the first power is 2, 2 squared would be 4, 2 cubed would be 8, 2 to the negative 1 would be 1/2, and 2 to the negative 2 would be 1/4. So we're going to get the same graph as we did just for an exponential. So we still have that same horizontal asymptote. And applying these points, we have 0, 1, 1, 2, 2, 4, 3, 8, and negative 1/2, negative 2/4. So just like every other exponential graph, here's the shape with base 2. Now how are we going to find the inverse? Well, to do the inverse, all we have to do is interchange x and y. So if 0 goes to 1, then we know that 1 would send it back to 0. It just flip-flops it. And if 1 goes to 2, then 2 has to go back to 1. And again, flip-flopping, so that'd be 4 goes back to 2, 8 would go to 3, 1/2 would go to negative 1, and 1/4 would go to negative 2. So what is this graph going to look like? Well, this is the graph of the inverse function. So we're going to have 1, 0, and then 2, 1, 4, 2, 8, 3, 1/2, negative 1, 1/4, negative 2. So as you can see, the inverse function, in a sense, is your log graph, and it bends over. Now we don't have a horizontal asymptote. We're then going to flip-flop those values, so we end up with a vertical asymptote. So the first graph is the graph of an exponential. So this is your exponential graph. And what we're going to learn is the next graph, which is our inverse, is the logarithmic graph. So exponential graphs start off slowly and then shoot way up, Log graphs grow really rapidly, and then they start to die off and bend over. So make sure you understand the difference between an exponential graph and a log graph. So now, definition of a log and so forth. So an equation, x equaling a to the y and y equaling log base a of x are equivalent. Meaning if you're in this form, which is exponential, you can change it into a log form and vice versa. So this is something you have to get really good at, going both ways. So the first equation is in exponential form and the second is in logarithmic form. So every exponential function of the form f of x equaling a to the x passes the horizontal line test. And if it passes the horizontal line test, it must have an inverse. And so now we're going to learn that that inverse function is called the logarithmic function. So the inverse of an exponential is what we call the logarithmic function with base a. So really important you understand. Highlight this, make sure you can go back and forth between the two different forms, from exponential into log and log into exponential. So number one says write the logarithmic equation in exponential form. How do we know if we're given a logarithmic equation? You're going to see log, log, log. So you know logarithmic equation, and we want to change it into exponential form. So when you read this, we read this as log base b of a equals 4. So log base b of the argument equals 4. So we know that the base is always going to be the subscript. It's that smaller number that's going to be written below the log. So that is your base. That's your base. And that's your base. So we have to start off with the base 3. And again, it's like we do a circle. Raise it to the 4th power and equals 81. So 3 to the 4th power equals 81. So I'm getting rid of the log by writing it as an exponential. So on the second one, we got to start with our base. Now we're going to go doing the circle in a sense the opposite way. So log base a of x equals 2, the base is a. So a raised to the 2nd power equals x. And that's how we change a log equation into an exponential. And lastly, we have 8 raised to the 4/3 equals 16. 8 raised to the 4/3 equals 16. We're not solving or anything. All we're doing is rewriting a log equation as an exponential. We got to be able to go both ways. So this is considered the exponential and this is considered the log. We got to go both ways. So at this point we went from the right side into the left side. So with the log equation, always find the base, start with the base, go across the equal sign, make it raise it to that power, and then come back and equal it to the argument. Now if we're going to go the opposite direction, we want to go from an exponential into a log. We'll see we don't see logs at all. That means they're all exponentials. We have to start off by writing log because we're changing it into a log form. And so how do we do that? Well, we have the log, take the base down below, of x equals y. So here's my base of 5. So log base 5 of 625 equals 4. When you write your base, make sure it looks as a subscript. So log base 5 of 625 equals 4. All of this is on the same line. So I don't want any floaters. I don't want things to look like any exponents are around there. It's all changed into a log form. So log base 5 is your subscript of 625 would equal to 4. So really, a log is just the exponent. Do you see that when we wrote it in log form, we equaled it to the exponent? That's all a log is. A log is just an exponent. So now let's write this next one. Log base 8 of 300 equals 8. Oh, sorry, equals x. So log base 8 of 300 equals x. Again, all this needs to be on the same line. Don't make any floaters. And what about c? We're going to have log base 7 of 1 over 49 equals -2. The only thing that goes below is the subscript of 7. Everything else stays on that same line. Now d looks a little bit different because we don't have a power. But you should know what the cubed root looks like as a power. So that's really 64 to the 1/3. So let's just make sure we remember some of these things. If we had the square root of x, that's really x to the 1/2. If we had the cubed root of x, that's really x to the 1/3. If we had the fourth root of x, that's really x to the 1/4. So anytime you have a radical can be rewritten as a fractional exponent. So we still need to change it into log form. So we'll say log base 64 of 4 equals 1/3. So log base 64 of 4 equals 1/3. But make sure you write the log first and make sure all of that is a sense on the same line. The only thing that goes below is the base of 64. All right. So if I said that a log was just an exponent, then let's try and do some of these without a calculator. I know some of y'all like to use your calculator to get all kinds of answers, but I need you to understand what a log really is. So what is a log? A log is just an exponent. So in our minds, we're trying to think of what power is going to make this work. So we ask ourselves, 2, here's our thinking process, to what power would give me 8? 2 to what power would give me 8? Well, the answer is 3. So log base 2 of 8 is 3. And we can check that out, again, if we're going to do some guessing later, but if we have our calculator, 2 to the 3rd, we know is 8. So then what about B? Our thought process should be 2, what are we going to think of, to what power would give me 64? Because we're thinking 2 to what power would give me 8. So 2 to what power would give me 64? Well, what is 2 to the 4th? Getting there. What's 2 to the 5th? And then 2 to the 6th. So we know our answer is 6. So log base 2 of 64 is 6. Now, if they keep going up like that, like for D, we say 3 to what power would give me 27? Well, the answer is 3 because 3 cubed is 27. So if the number keeps getting larger, that's not so bad. But what about like C? Log base 2 of 0.0625. Well, that says 2 to what power would give me 0.0625. Well, we can't go 2 to the 1st, 2 to the 2nd, 2 to the 3rd, because that just keeps getting bigger and bigger. But what about 2 to the -1? Remember, that makes it into a fraction of 1/2, which would give me 0.5. So about 2 to the -2. All right, we're getting there. 2 to the -3, and then 2 to the -4. We finally get 0.0625. So it's a little bit of a guessing game. So you might want to make a note that if your base goes into a decimal, think negative exponents. Again, if your base goes into a decimal, think negative exponents. Now, what if your base, which is 25 on E, to what power gives me a 5? Well, that's not going into decimal, that's just going from an integer that's bigger to a lower integer. We'll think about square roots. What is the square root of 25? It's 5. And what do we represent square roots as? As fractional exponents. So this would be just 1/2, because the square root of 25 is 5. So log base 25 of 5 would be 1/2. And then on this one, we have 10 to what power gives me 100,000. What do we say? Well, if we go bigger, what about 10 to the 4th? Well, that would give us 10,000. So 10 to the 5th would give me 100,000. So the answer would be 5. So again, if your base gets larger, then you know it's just going to be a nice integer value. If your base goes into a decimal, then think negative exponents. And if your base is bigger but goes down to a smaller nice integer value, then think fractional exponents. So I want you to try the rest of this on this page, and I will give you the answers in the next video. But definitely try those because of the fact that you want to make sure you understand how you can get to these answers without a calculator, so you understand what a log really is. All right, so now we're going to do some properties. With properties, some students ask if I have to memorize all this, and I sure hope not, because if you try and memorize, you're not going to understand. You have to understand the concepts, and then these properties are okay. So for example, this says a to what power gives me 1. So your thought process says a to what power gives me 1. Well, anything to the 0 power is 1. So log base a of 1 is 0. When you see log without a base written, that's automatically a base 10. So 10 to what power gives me 1? Same thing, 0. And we'll talk about this one in just a little bit. So on the property of number 2, log base a of a is what? Well, that says a to what power gives me a? Well, that would just be to the first power. So log base a of a is 1. And we're going to have to use these properties when we get into condensing and expanding and also into solving. Now looking at number 3, we say a to what power would give me a to the x? Well, the answer is just x. And then on property 4, if log base a of x equals log base a of y, if the bases are the same, then the arguments, we say x and y are considered arguments, then the arguments have to be equal. Some students go, oh, the logs just cancel. No, they don't cancel. It says if the logs are equal, then the arguments have to be equal. And number 5 is kind of the most interesting one. When you have an exponential raised to a log, as long as the exponential that's raised to the log has the same base, those are inverses of each other. So they just cancel each other out and you get back what you started with, which is x. But the bases have to be the same, and they will be. So for base 10, all of these properties stay the same. This again has a base 10, it's not going to show. So we say 10 to what power gives me 10? Well, the answer is 1. And 10 to what power gives me 10 to the x? Just x. And if the logs are equal with base 10, then the arguments have to be equal. And if 10 is raised to the log base 10, then they're inverses of each other. They just cancel each other out, so you get back what you started with, which is x. Now here's one that a lot of students don't realize what ln represents. They think it's, well, they're not sure. But ln actually, so you're never going to see something being written as log base e. They're going to call it the natural log. Remember in the previous section we talked about what e was? E was approximately 2.718. With log base e, that is rewritten as a natural log. So you'll never see log base e, you're going to see ln, but you automatically think it's log base e. So this says e to what power gives me 1? 0. And then e to what power gives me e? 1. E to what power gives me e to the x? X. So really all these are the same. So why am I showing it to you in different ways? Because I want you to understand that all these properties hold true for base a, base 10, going to be true no matter what base you're in. So if the natural logs are equal, again they have base e, then the arguments have to be equal. And if e is raised to the natural log, those are going to be inverses of each other. They take you back to where you started, so your answer is x. So let's look at 1, 2, and 3. Use the properties of logs to evaluate the following problem. So we're just going to try these properties up here. So log base 7 of 7 would be property 2. It's just going to give you a 1. Again, your thought process says 7 to what power gives me 7. Number 2, log base a of a to the third is property 3. So you're just going to get a 3 out of that. Because log base a of a are inverses, they cancel each other out, and you're left with your exponent 3. Number 3, we're going to evaluate natural log of e to the negative 2. That's also property 3. Natural log has base e, so they're inverses of each other, and you just end up with negative 2. So we saw what the graph of a log looked like, but let's go ahead and do just the parent function, which is the basic log graph. So a basic log graph will always have a vertical asymptote. All log graphs will always cross at 1, 0. And this is not what you'll do on the test, but I do want you to understand that all log graphs just bend over and head off to that direction. But they don't ever go straight horizontal, so you'll continue going up and up and up and up and up. So your domain says go from left to right, and we haven't used any of this till we get right past 0 to infinity, but we can't use the 0, so it needs to be in parentheses. Your intercept 1, 0. Your range goes from bottom to top, and you'll see that we go from negative infinity all the way to positive infinity. And your asymptote now is going to be a vertical asymptote, and vertical asymptotes are x equals. Make sure you put the x equals, If you don't put the x equals, it's not correct. You need the x equals for vertical, you need y equals for horizontal. So let's go ahead and graph number 1, and then I'll have you graph number 2 and bring me back the answer so we can see everyone's okay graphing a log graph. So first things first, we're going to graph the parent function. The parent function would be f of x equaling log base 4 of x. Now we know what the plus 5 is going to do to everything because we know about transformations. So the plus 5 is in parentheses, so it's going to move everything to the left 5. But we need to graph the basic log graph first. Well, to graph the log graph, we probably should change it into an exponential because it's easier to find points. So 4 to the y equals x. So 4 to the y equals x. So all we're going to do is change our log form into an exponential form because it's much easier. Now normally we plug in values for x, but do you see that it'd be easier to plug in values for y? So we're going to plug in a -1, 0, 1, and 2. Much easier to plot values for y and plug it in to find x's than to plug in for x. So I'm going to have 4 to the -1, which is 1/4. 4 to the 0 power is 1. 4 to the first power is 4, and 4 squared is 16. So your basic log graph, again, always has a vertical asymptote. 1/4 -1, 1 0, 4 1, and the next one's not till 16. So 10, 11, 12, 13, 14, 15, 16, 2. So it's going to bend over really quickly, but again, it's still going to continue going up, just not as fast. So there's the basic parent function with log base 4. Now the plus 5 is going to move everything to the left 5. So opposite of what we think because of the parentheses. So now make sure that you move the asymptote left 5 and every point left 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Somewhere about there. So here is now the graph of my log with base 4, parentheses x plus 5. So what is your domain? Well, going from left to right, we're going to start at -5 and everything that's greater than -5, but we cannot include -5, so make sure you use parentheses. Your x-intercept is now at -4, 0. And your vertical asymptote is a vertical line. Don't forget the x equals, so x equals -5. So I'm going to want you to try number 2. I'm going to start you off by telling you that it's f of x equaling log base 3 of x. You're going to do your circle, so 3 to the y equals x, and then make your table with y being -1, 0, 1, 2, and so forth. So then if you do those, when you plot them, you're going to get the same parent function as above, just a little bit more up as you curve, and then move everything to the right 3.